Ladies and gentlemen, welcome to my second video of the Swarm Robotics tutorial. And now I will explain about the boids algorithm. As you can see in the previous video, I talked about what boids algorithm is. First, the boid algorithm consists of three things. The first is separation. Every unit has to avoid each other. Then we have cohesion, where every unit has to follow the same path. And then you have alignment, means every unit has to move towards the group. How do we do that? Well, I'll show you the code and the simulation right now.
15 minutes later.
Hello everyone. Okay, welcome. Now this is my Visual Studio Code, and now I will start with the Python. I'll start the tutorial with Python. First we make main.py, where we could write define and main.
7 hours later.
Now finally, and how do you do with void? It's we run the void into a loop, and if we find a void first, then we find the centroid of the void for every angle. You can see it. We use the current void angle, and we use the other angle, and we divide by 2. We equal with this, and this allows us to align. And sorry for the spelling problem. This we have this. Yes, do we do that? Of course we do. Now finally we self.cohere. How much we have to cohere? So now we have voids and we have cohesion distance to 50. And first we define the average x and average y to 0, and we have count. And then we have voids in voids, and we have the x and the y, and we have a distance. And if the distance, after we calculate the distance, and it's less than the cohesion distance, which is 50, we increment the average distance by x, y, and we increase the count. And if count is greater than 0, we divide by average x and y with the count, and then we append to self x and self y. And this is our update function. Now, what do we do? Do we run it? Let's try again. What's happened?
1 eternity later.
We can run the game just fine. Look at this. Look at this. So many voids. Look how they converge. It's so good. But there is a fatal flaw. Let me show you. What is the fatal flaw? Well, let's increase to 500. What will happen if we set to 500? Look at this! Look at this! The performance, it's garbage! The performance is garbage! Look at this! Let's turn it off. How do we fix this? Well, let me show you, my little friend.
15 minutes later.
Usually when we have the void right here, and we have a void right here, and here, and here, on here, this will consider all the neighbor, all of them. It just knows all of the neighbor if they are within the circle. But this one is also inside the circle. It will also look at this one, this one, this one, and this one. And we also do with this same one, this one, and this one. You know what I mean. And because right now we have 5, we have to do approximately n squared complexity. No, it's not n squared, it's O squared complexity. And it is very bad. It is very bad. You know, O2 scales terribly whenever you add more units. How do we solve this? Well, it's easy. We use this boxed bucket things. What if instead we calculate all this, we just put all of them, each of them, in the buckets. Now, instead of we count each of the agent, we count how many agents are there in the bucket. So this one has 1, and if there's more bucket, we don't consider it. We skip that. And if this, for example, this has no empty. If this is empty, we skip. And if this is not empty, we count to 1. We also count to 1. We count to 1. But this one has count to 2, so we consider that. So now we calculate this. So right now, this one is invisible to this bucket. This and this cannot see each other because they are far away according to the bucket rule. But these two, they are not far each other because they are inside the same bucket. But we can do better. What if we have all the nodes right here, all the boids right here, all my little boys, all my little cute little boys, and we have divided buckets right here like this. How do we do that? Well, we calculate this one has 1, this one has 1, this one 0, but this one has 4. But we don't do that. We also take the overlapping because when we do that, we shrink it down. We shrink it down to this, and we shrink it to this. But this one don't get shrunk. This one gets ignored. So this bucket, it will have a new counter which consists this to this and this with each other. But this one will have all the 4 calculated against each other. So the distance between, but what about these two? How do we consider these? But this one belongs to that. Fret not, my friends. We'll get it to right now. We just ignore this bucket when we count the half bucket. We ignore that. We just merge this bucket with it down below. And this one's too. This one has a bucket with neighbor. We merge with that, and we merge with also that. So the logic we do call K means classifier, but I don't know if this is classifier. K mean, we don't know if it is K mean classifier, but I called it the bucket distance, whatever I call this bucketing. So it's much easier. I call this bucketing. Now let's go back to the code.
One eternity later.
Now, ladies and gentlemen, something interesting is happening. Now we wire everything into the game. Instead of we run the main function, the game itself in the main function, we run the simulation in this game. Look at this. Look at what Cloud Code did to me. It did something good. First, we have the grid parameters. We can tune it. First, we have total main buckets. We have a number of sub buckets. We have bucket overlaps. And then we have the processing line threshold. And then we have sub bucket overlaps, which means we'll keep the boundaries of the buckets. This is my main bucket. This is the main bucket's dimension. This is sub bucket's dimension. And we see sub per main is S. We calculate the columns, total columns, and we calculate total rows. And we calculate each self in width and self per height. And then we fill in the buckets. And this is my boids. And we fill in all the boids. Then we find a locate. This is my location function, which means where am I? If the row and column. Then we calculate the threshold. If it index and sub-index. And then we return process line and sub buckets.
7 hours later.
And if there are multiple buckets where each has a couple of voids, the voids in one bucket will never see the voids in the second bucket. So this will hopefully speed up the game. Let's see what we got. Look! It sped up the game. Wow. Beautiful. Before that, it was so janky and slow. Now we got a speed up. Let's add 10 times as much, like 5,000. What will happen? Will it tank the performance? Oh no. Oh no, we got a performance tank. We got
7 hours later. One eternity later.
Hello again. Let's see, after a couple of while of waiting, now we got to optimize. Now we have optimized the code. Take a look. We have 5,000 boids flying around, following after flux while avoiding each other, but they want to cohere together. And you can see this is a 5,000, and now it runs much better. But since this is a Python, you know, you can see it runs much better. So, how did it go better? Well, let's dive in. This is my main function. It runs initialize the Pi game. It set up the width and height, which is full HD, and it display the boid simulation name, and we start the clock, and then we initialize the game, the game class, which is the set up the width and height and the number of boids, and this is my game G. And then we run the loop. While we run, we fill in the background color, we update the game, we draw and we display, and then we take in frames per second. But if you want to close the game, like for example, sorry about that, and if you want to close the game, like if I place here, for example, Pi game is quit. If it is in event time, we run false, and if we press key down or key escape, we also set it false, and then we exit the loop and we stop the entire game. Now you're wondering, what is this game function? What is the game class? So it's not a function, it's a class. Let's get in there. This is my game class. We take a width, height, and number of boids, and then we have a frame count, which is set to 0. The boids is defined as a set, where we have each boid here, and this boid is defined here. It has its x and y position, it has a velocity, but it also has max speed, minimum speed, and maximum force, and it also has an angle. And it has a property where we return the angle. We have also a steering function, where how much we have to steer, and then this is the separate function basically how much the boids have to separate, how much more close they have to be each other before they separate. We have x-axis y, we have count, we have consider the other boids, we have sub boids of x. Yes, basically nothing's changed here. Cohesion is left unchanged, alignment is not changed, but we also consider distance, we also use the steer. Also cohere means we also steer towards the center. And this is our update function. We consider the separate, align, cohesion, sx, align, and cx, cy. And this is our total function, sx, ax, and cx. This is our velocity, and we consider the speed. And if we found the speed, we vx divided by speed times max speed, vx speed, and then we update our position. And if width is none, we modulate the width, and we also modulate the height, and then we draw the entire thing. But anyway, let's go to the game because that's more important. First we get the position of each boid, and then we also get the velocity of each boids. Because we have the memory bandwidth, boids need 3 significant digits and well within the range. That's right. To increase the bandwidth, we cut off the digits, so the bandwidth becomes half, so we can have more stuff in it. Now we run the update, but unlike the update in the boid, the game has its own update function. Take a look. First, we set the n equal a number of boids. We set frame count plus 1. Then we calculate the Qt node. What is the Qt node? It's the quad tree domain. What is the quad tree? The quad tree is a grid that is subdivisible by 4. For example, you have our giant square, but inside the square you have 4 small squares. And if there is a lot of element, if one of the square, that square becomes divided by 4 again into 4 subsquare. And if 2 of these has more elements but not the 2 lower, then those with more squares get also divided into 4 square with a finite number of subdivisions. Then that's what we call the quad trees. It's basically dividing a bigger square into a smaller square inside, like some fractals, if you know. Now let's check the Qt node, because this jumps right there. And now we take the slot, the x, y, w, h, depth, item, and children. What is it? Let's define it. X is the x-axis, y is the for y-axis, w for w, and h is for depth. And depth means how many division do we have. And item means what does it contain. And the children is the subdivisions itself. If there is children, we go to a route. If there is not, then we append the item by its index. It's a b and by. And then we also look for the threshold, density threshold. If the size of the items is larger than the density threshold and the depth is less than a maximum depth, we subdivide. What does subdivide does? Well, it takes the w multiplied by 0.5. We make them halves, and then we add to the x and y. We consider width and height, multiply in half, then we add x and y to width and height. And then we define 4 quad tree children. The first quadrant is to self x as y plus hv h for h and depth plus 1. Then we have max x and max m width and ls ly, then we have sub x and y and mx and y. So we have 4 sub quadrant: top left, top right, bottom left, and bottom right. Then we route the items inside. So let's look at the route. Routing does like that. It's just mx, the maximum x, is self plus x plus self.x plus self of its width in half. Same with the y. Y is height in half, and q1 is 1 if the bx is equal larger than mx or else 0. It's a Boolean logic. And 2 if by is larger than my or else 0. Then we set out children where qi is the index. If the excuse me for that, but okay, the children of the index is qi. It's actually an index, sorry about that. Then we insert the index number and bx and by. But what is the query? What does this do? Collect leaves and neighbor. Okay, we go back. There. So what about the insert? For every I in n, we insert the position. Insert the position, for example, the number of what we call the boids, not the boids itself. Then we look at the insert. It basically idx, ids. Yes, we already went through. Yeah, let's ignore that. Then we consider the leaf that it's empty, and then we collect leaves and neighbors. What they have this one is the output, and this is the root node. If there is no children, if there are items, then we find a candidate, and root node, then we query those candidates. And then we set out leaves to items, how many items we have, and then their candidates. Or else, if there is children, we collect leaves and neighbor recursively. If child is in children, then we recursively call the out leaves equals the root node. So now what about the forces? Forces is how much we pressure. Forces is where how much acceleration steering it does. But right now we set to 0, and then we want to do some high throughput. How do that? We have the items, we have candidate in this leaf data. So first we take I for item and j for candidates. Then we compute the delta matrix via continuous vector slices. And now we optimize this by raw square distances, first to avoid expensive square root. So how do we optimize? We just well, it's simple. We just calculate the raw square distances, and then we mask our self interactions. These two, since we ignore the square root because square root is highly expensive operation, we just multiply and squared is just the multiply by itself, and it's much faster than division or square root. Then we have separation. We have a distance squared is equal to separation r squared. We have square, and then we find any. If we set any, we set square. Safe distance squared is where str. I don't get it too much that, but then we have reparation, yes, and then we have reference and square reference magnitude non designer force magnitude and force yes. No power. Yes, I get it. I get it. This is simply square. This is square. It's a math. This. And f square. Then we align. Ah, yes, separation. This is the separation. Ah, yes, yes, yes. This is the separation rule. You see, this is the separation rule. Oh, I'm so stupid. But unlike with the function call, we all make inside the entire update function is to optimize. And now we make an alignment. This is alignment rule. This whole thing is alignment rule. First we find the alignment vector, we find its magnitude, we find norms, we find the desired alignment, because we want to see what is the central. And then we find the force, which is the normalized magnitude, and then we set the forces where n pi where we calculate the forces for the alignment. This is the force we calculate for separation proof. We need to show and we don't hit each other. This is where we want to move towards the group of the other boids, and this is the cohesion where we align our angle where all moves into the same direction. Then we calculate the velocity, which is how much force we apply, and the speed. What is this? And the speed is calculate the velocity is normalized velocity, and we set the safe speed is that speed. If speed is greater than 0, we set the speed, or else 1, because we won't want this speed to be bigger or less than 1. So now we set the velocity is where speed is equals max speed. If speed is greater than max speed, we set it down, and if speed is less than minimum speed, we set it up, we throttle up. Then we calculate the position, we find its weight and height, and then we make some frame count, and finally we draw the whole things, and voila, we got this, a nice 5,000 boids simulation. But you are wondering, why is it not so smooth? Well, my friends, this is a fault in Python. It is an interpreted language, not a compiled language. So, if you want to do some compiled language, we write this code in C++ or in Rust. Follow me in the next video.